I am definitely feeling like I should have remembered there was a symposium today. So if I sort of keel over halfway through, I apologise. I don't even drink wine anymore. It was the Calvados that Ian supplied at the end that's the bit of the disaster. So I'm not looking quite as perky as I am in this slide. This slide is up just because this is Edinburgh. You can actually see Arthur's Seat in the background. And actually, in fact, as well, that's the King's Building site. So it's a beautiful place to live and work. And I haven't escaped it since I came back, and escaped here, actually. So I'm going to tell you a short story which comes from the last 10 years of research in my group. I'm going to tell you a little bit about Raman Spectroscopy. I'm going to tell you about Raman Spectroscopy in vivo and why I think this is important and relevant to MedChem. And so I was very excited when I read this JAX paper in 2011, because I think, like a lot of academics in one particular area of chemistry, we'd done quite a lot of click chemistry. We were early adopters. We put proprietary groups on things. We clicked on a fluorescent A side. This was all really exciting. And then I found this paper where you could take ethynyl deoxyuridine. It's a thymidine analog. It gets incorporated in the DNA inside the nucleus of a cell. And you could image it directly just by imaging the alkyne. And so what you're doing here is, in Sodioka's group, what they were doing is click-free imaging just by rastering across the cell, taking individual spectra for each pixel, and then here's converted that into a map of different properties. And I'm going to lead you through some of the chemistry behind this. So I thought this was really, it was like, hey, I don't have to do that click chemistry. This looks good. I can stick a propargyl group on something, and then I can just image it directly. Not quite that simple. And you'll also see that this took 49 minutes, which is not the best. Okay, this is using something called spontaneous Raman. So we all did infrared spectrum, because if you want to get your molecule published in Orglet or wherever it might be, part of your routine characterization is to take the infrared spectra. So we're all very trained in vibrational spectroscopy. And you're used to the idea that infrared spectra, you need a change in dipole moment for that for you to be able to see that stretch, and that's what you record. What we're not quite so used to is Raman spectroscopy as synthetic organic chemists. And in Raman spectroscopy, we're looking for a change in polarization. And so we've got a different kind of set of bonds that give us nice big signals in Raman spectroscopy. It's great if you're going to use this in a biological system, because water has a very weak cross-section. And so we don't get lots of interference from the background, which is water, which, of course, there's a lot of water in biological systems, so that's quite important. The downside is only 1 in 10 to 7 incident photons are Raman scattered, which is one of the reasons why this image on the left took 49 minutes to acquire. Okay, a little bit of basic background. Vibrational spectroscopy, obviously we know it depends on the bond strength, okay? I think I had 4, 5, 6 maybe different carbonyl stretching frequencies in the course of my PhD molecule, ebolactone, because, I had a ketone, I had an ester, I actually had a thioester, I had an oxazolidinone, I had various, functionalities as I was doing my aldol chemistry. So I was quite used to vibrational shifts, okay, of my carbonyl. So what I've shown here is just an example from our group of a modified PLGA. So that's an FDA-approved polymer that's biodegradable. Where the yellow star is, normally that would be a CH3 group from lactic acid. So, and you see the stretch in the black spectrum with the yellow star. That's where your CH stretches occur. You're quite used to the idea they're at about 3,000 from infrared. If you replace that CH3 group with a CB3 group, what you're doing is changing the reduced mass about that bond, and so you get a massive, because that's a big change, that you get a massive shift. So that red shift that's shown with the red arrow, you now get vibrations, where the yellow star goes in the red spectrum. If you put an alkyne into that PLGA, you get this beautiful sharp signal. Okay, which is really nice, and I'll talk about where that sharp signal occurs in a minute. So, a little bit of background: changes with bond strengths, clearly changes with isotopes. So, no good if it takes you 49 minutes to acquire an image. That's not going to be much use if you want to follow things in a biological setting. So we're not going to use spontaneous Raman, which is what's shown on the left here, where you use a pump beam to excite to a virtual excited state, and you're actually measuring the Stokes output, the wiggly red line. What we're going to do is look at using stimulated Raman scattering, and so we're going to have two lasers which we tune, pump beam and Stokes beam, to the vibrational gap, and then we just look for a change in either the Stokes or the pump beam. Okay, so and that coherent spectroscopy actually then increases your signal, and you get a 10 to the 7, 10 to the 8-fold enhancement in signal. And so suddenly we can start to do things because we need less time on each pixel. We can start to do things in a realistic time frame. And unlike the coherent spectroscopy that you may well have heard of, CARS, unlike that, there's no non-resonant background, and we don't see any distortion of the signal relative to the spontaneous spectra that I've shown you on the left there. So we can take a spontaneous spectrum of our molecule and know where we're going to see a vibration in our SRS image potentially. Okay, I couldn't have done any of this research without Martin Lee, who's a bioengineer, and without Val Brunton, who has a chair of cancer therapeutics, both at the University of Edinburgh. And the story, which I don't have time for, it's quite funny because I read this paper, I discovered we had one of these microscopes that I needed, in Edinburgh, and then it took me about 2 years to persuade them that actually they shouldn't just be looking at tissues, but they should be looking at drugs as well. This is crystal. It's not a beautiful microscope like you buy in a box. Okay, so this is crystal at the microscope, which you can see as a series of components, and which we've put together, and then bits break. As soon as you have more than one laser, it's a bit of a problem. Bits break, you have to get it repaired, goes back to Germany, comes back, whatever. But this is, you have that nice time frame when everything is working and you can take some nice images. So what I'm going to tell you about now is what you can do. So if you grow cells, you spin them down, you put them on a microscope slide, you can just record a spectrum of the cell, okay? And that's what the spontaneous spectrum at the top is there. In blue, shaded in blue, is what we call the cell silent region. So there are no cellular signals in that region. So between 1800 and 2800, not surprisingly, there's nothing in there. Quite a nice region to target as a chemist because you get very good signal to noise ratio if you have a signal in there. You can see familiar stretching frequencies, carbonyl, but also I've highlighted CH2 and CH3. So CH2, if you look at lipids, obviously they have a lot of CH2s, and if you look at proteins, they have more CH3s, and so you can kind of split that CH region into a protein and a lipid region, which is what we've got down below. So we have tuned our SRS microscope to look only for vibrations corresponding to that CH2 vibrational frequency, and you can see it 2840, and then we've moved to tune to the vibrational frequency for the CH3s, and we can plot the lipid and the protein inside that cell. It's not coloured because it doesn't have a colour, okay? But we're used to seeing things in colour, so maybe we should just have a little bit of a think about putting some of these images into colour. So we can, for instance, now we've got these two images, we can start to do some image processing, and one of the things that we can do is do different spectra. So if you take the CH3 image and you subtract CH2 image, you can see that the nuclei and nucleoli stand out very nicely. If you plot the difference image and the CH2 image, one on top of each other, okay, in different colour channels, we've got something that looks quite like a fluorescence. You'd think that we had labelled that cell. We haven't done anything. All we've done is just measure the molecules that are in the cell with a bit of chemical knowledge. And then if you present that to a biologist or a medic, that wouldn't look very familiar. So if you just take that blue and green and recolour it to more like an H&E type, all you've done is change the colours for the information, the chemical information that you have, and you can see that that image becomes an H&E stain, okay? Only we've had, it's a very rapid process, we've just had to acquire two images, we've done no staining, so we haven't altered any of the physical properties, and we can do this on live cells, okay? Now, okay, I'm a chemist, so I can go and look at a much smaller fraction of molecules than Jonathan can, but maybe we'll go to him sometime soon and go bigger. But if you look at the available bioactive ligands in the PDB, a very brief analysis, and actually, do you know what the amazing thing about the pandemic, although there have been so many negatives, is that our PhD students are now totally used to the idea that they should go and look at data. And so I am sure I could ask any one of my, in fact, I've actually sent one of my PhD students, I said, go and update this for me, please. I've got this in my talk, but it's, this is from 4 or 5 years ago now. Just go and update that. And here's the tutorial. Emble have got a tutorial online. It'll only take you half an hour to go through the tutorial, and then you can do this for yourself. And you know how smile strings work. So, that's the amazing thing about PhD that PhD students have learned through the pandemic. Anyway, if you look at this graph, you can see that only 5%, 10% of drugs, okay, you guys, you don't put that many alkynes or nitriles in them, which is a bit of a shame, because those are the ones that fall in the cell silent region. If we just go quickly back, you can see that nice region where I'd love to have a signal because I've got good signal to noise. But being a chemist, I'm going to assess the tyrosine kinase inhibitors that Ray has just written off. I'm going to assess the tyrosine kinase inhibitors and pick one. So I literally went to my colleagues in cancer biology, to Val, and said, we should work with this compound because this compound has an alkyne flanked by 2 aryls, and so it's really polarizable, and so we're going to get an enhanced signal. We know we're going to get an enhanced signal. And it comes at 2221, sorry, and so we can start to image it. So what I've got here is just a volume viewer of a series of Z-stacks going down through the cell. And all I've done there is plot the concentration of ponatinib inside the cell. So we haven't labeled ponatinib, we haven't added fluorophores, we haven't done anything. This is just ponatinib inside the cell. And obviously, if you then take the signal intensities at each of those points and you translate that, you can use MATLAB to generate an intracellular concentration and find out that it's quite good with the one that the mass spec guys tell you is the intracellular concentration, but we know where it is rather than just being in the cell kind of thing. And then we can start to do some biology, and I don't have time to go into all of the biology kind of thing, but what we did with colleagues from the Beats, and we had a ponatinib-resistant cancer cell line, KCL22 cell line, and we could start to look at the resistance mechanism in terms of, okay, how is this resistant cell dealing with ponatinib that's not a mutation, but what is it actually doing? And we found out that, in this instance, there was more ponatinib in the lysosomes, and there were actually more lysosomes as well. So the biogenesis of lysosomes had actually increased too. And the next bit may or may not work. Oh, come on. Let's see. I've tried. I hate to say it. No. Well, it skipped it. Okay. I had a nice rotating. It doesn't matter. We don't have time. I am going to keep going with tracking. So tracking. So for me, tracking was taking that compound that I had, it going into the cells, viewing it directly kind of thing. I can track also what might happen to it in terms of reactions. So I have 2 colleagues in Edinburgh, Mark Bradley and Asir and Chetty Burketta, who are both looking at ways of making molecules inside cells or in a tumor or cell environment by bringing them together with things like click chemistry. So you take 2 smaller components that might more easily diffuse into a cell, and then they react together. So I've always been fascinated by click chemistry and looking at reaction kinetics. When you have one of the world's best kineticists in your department, you go to him. So this work was done in collaboration with Guy Lloyd-Jones. And so I said, okay, well, if we put this EDU inside a cell, are we going to be able to look at the kinetics of click reactions actually inside cells? Those of you that have seen Jason Chin speak, you know that he has these lovely rainbow slides. I have them in my undergraduate lectures before he published them because he gave them to me. These lovely rainbow slides of relative rates of bioorthogonal reactions. And the problem is that when you go to all of those references, you discover that these kinetics were actually done in, at best, some kind of buffer, but mostly in like water or water methanol or water acetonitrile or whatever. So not actually in a cellular environment. And it'd be really interesting to view these reaction kinetics in a cellular environment. So we first just did it in solution. This is then some work doing it using standard Raman spectroscopy. We're tracking the disappearance of that alkyne peak. And you can see it's disappearing with time. And we just use the area under the curve to actually look at the kinetics. It's all standard. We published it in Faraday discussions. And then you can do the same kind of thing. So if we look, these are now our own images of EDU taken on the SRS microscope in a matter of, one of these frames then takes, I think it's about 10 microseconds to acquire. So we can actually then track the kinetics by taking sequential images with time. I have put on the bottom of this slide, I won't take too long on it now, but it's not quite as easy as just stacking them and seeing how fast the signal goes, okay? Because you get focus drift, alignment issues, and intensity issues sometimes from your laser fluctuations or whatever. So we have to do a bit of background correction using the CH3 signal from the cytoplasm in order to be able to kind of like background correct and sort out the data. We've got some lovely data. I have failed yet to manage to convince anyone that to publish this, okay? We had a couple of goes in Angamanta. So if anybody comes to me afterwards, this is an advert. I'd love to publish this data. If you think you could use it somehow, that would be really cool. Come and talk to me, please. Okay, what about dual color imaging? So obviously, could we put more than one alkyne into this cell silent region? You've seen EDU already, I've shown you that. And so then the other motif that's used are what we call these Bis-Aryl Dye Ions. So a diene in the middle flanked by aromatic groups on either side gives you a really nice signal. And you can see that there's a significant shift between the EDU, which I've highlighted with the blue arrow, and the baddie tag, as we call it. One of my PhD students had a baddie is a goodie talk title. So the baddie tag. And so I'm now going to talk about how you might trace things, like adding something on to be able to trace them rather than being able to track the compound directly. So you can see dual color imaging. Whilst I'm talking about it, you can also do dual mode imaging because we have a 2-photon fluorescence capability on this microscope as well. So we can look at things like standard fluorescent trackers for organelles and see how that matches with compounds that we're actually tracking inside the cell. What about multiplexing signals? So one of the leaders in the field is Wei Min, and this is a beautiful paper, Nature Methods paper, where he talks about multiplexing. So the nice thing, and two things that I've got on here, is that if you look at the full width half maximum, is that the right way? I always hate, yes, I always hate that acronym, but basically how wide each of those peaks is. You can see it's about 15 wave numbers. Now that is way smaller than any fluorescent signal. So the opportunity exists to put lots and lots of signals in that cell silent region, potentially, if we can work out how to do it. But the problem is, this is a beautiful paper, but you can always hide things. And when you know that something's been hidden, it's like, okay. So the issue with this is that each of those signals has been normalized. And then beautifully plotted in origin, one above each other, but all to a height of 1. And it masks a signal intensity issue because, in fact, there's a massive increase in signal intensity that I've coloured below. So using our own DFT calculations and data, that's just showing you the wave number that we calculate DFT. The calculation's doesn't quite match experimental, but it's not bad. But you can see the intensity, and that really masks, and actually it is written in the paper. And Wei Min gets around this by using 10-to-1 concentration ratios of things in polymer beads, but we were interested in being able to track things similarly with, if you talk to Martin, the man who's actually running the microscope for us, he doesn't want to have to retune the microscope in terms of laser intensity every time he takes an image, because basically that causes problems straight away. You don't get comparable data if you start having to do that. So what we wanted to be able to do was really try and broaden that colour palette, have a blue shift, a red shift for the colour palette, but sticking at the same signal intensity. So this is again DFT kind of data kind of thing, but what we want to do is put either electron poor heteroaryls on one end, and we've been using a whole range of them to give us a blue shift, or put electron rich aryls on the other end, and that again gives us a red shift. Okay, so we can spread the spectrum. I haven't put the data in because we are about to publish this. We haven't quite published it yet. You can imagine, as a lot of people working in pharma, that one of the advantages of this is also that we are also playing with the log P, because these are a bunch of grease. If you look at the Bis-Aryl Dye Ion tag, it's not a great tag in terms of thinking about trying to put it onto a pharmaceutical compound, perhaps. So we are playing with the log P at the same time. Also, we have stacking issues. So Craig Stephen, who has a case award with AstraZeneca, has, amongst other things, been exploring making these molecules less flat, increasing the FSP3 to see if we can counter some of those stacking issues. And certainly you've got BADI and shown, this is from the crystal structure above, and tetralin and BADI below, and we do see a significant difference in the solubility of those signals. Okay, I had to have one synthesis piece in, so here it is. The difficulty with making non-symmetrical alkynes, of course, is it's actually very easy to do a Glaser coupling where you just bring two equivalent alkynes together, and you can play with those kind of things. If you have 5 equivalents of one component and one of another, if you want to have non-symmetrical ones. The reaction that we use, though, by preference, is this Chodkiewicz SP-SP coupling, where we have one alkyne. He's coming, but I can do it too. Where you have one alkyne as a bromide, and we're going to bring those two alkynes together. Now, we get a massive load of homocoupling if we do this, except in the presence of the ley ligand. And so this is an underused ligand, which I think it's been developed to enhance the reductive elimination step. It worked better than using tert-butylphosphine. It worked better than using, so any other of the phosphines that we tried to use, it worked a lot better. I'm looking at Gail's face here. And so it worked a lot better, and it really helped us with these couplings. Right, you're all right, because this is my last bit, okay? So, where are we going now? We're looking at labelling other therapeutics. T cells, Ray, what a great choice. Yeah, okay, so we're looking, so that's the work of Ander in my group at the moment. He's working with GSK, and we're looking at T cells, where the issue is that we want to make sure we have signal longevity. There are advantages in using Raman over fluorescence because we don't see photobleaching. We're also working at labelling antibodies with Connor Evans, who's in the Harvard Medical School. So there we want to use specificity, and we're trying to match tags to do a kind of like barcoding. And we're just about to start some work on antisense oligonucleotides as well. We've all been in this situation. This is thanks to my group. I have to say thanks to my group. And all these people for funding. And a pretty picture at the end, just to say thank you very much, Ian, for all your help and support over the years, and enjoy your day.